Hi everyone, it's time for the weekly question and answer. And today's first question from the discussion boards are from Kayla, and I'm paraphrasing her here, but she asks if you can't use distillation to completely purify a minimum boiling azeotrope, how else can you purify it? The answer is that you would have to find a different way to do it, and one of those ways might be chemical means to purify the substances in the mixture. For instance, you might mix in another reactant that would allow you to precipitate out one of the components in the mixture. Let me give you a real life example for this actually. If you have a mixture of water and ethanol, this is actually a minimum boiling azeotrope. And it is not possible to use distillation or a still to purify it more than 95% ethanol, interestingly. So no matter how many times you distill water mixed with ethanol, you cannot get it higher than 95%. So the way that they would make pure ethanol or completely isolate the ethanol is to mix in some sort of desiccant into the mixture. And the desiccant will react with the water, settle out as a precipitate, and then the ethanol itself can be decanted. And it's anhydrous ethanol. It would be completely pure ethanol. Okay, the next question is asked by Carter, and I'm really paraphrasing him here, and hopefully I've captured the essence of his question. He's asking about non-ideal solutions, and we saw for non-ideal solutions that when the delta H of mixing is deviating from zero, especially where it's less than zero, he's asking if the increased vaporization or the lowered boiling point of a non-ideal solution where we've got a negative delta H of mixing, or it's endothermic, caused by the heat released or the increase in temperature. Okay. If I understand you correctly, you're asking when two substances mix and it's exothermic, sorry, I may have said endothermic, but I meant exothermic, then is that release of heat what causes the vaporization as a result of the change in temperature, say, of the system? I believe the answer to your question is no. We can assume that the process is isothermal and we will still get increased vaporization and a lower boiling point. So if I understand your question correctly, the answer is no. The increased vaporization is caused merely by the weaker intermolecular interactions and not a result of the kinetic energy released or the heat or the rise in temperature. Okay, the next question came from Allison, and she asks, why do we divide by nu to get the mean ionic chemical potential mu plus minus? And the formula that she's talking about is equation 10.15, where I told you that mu plus minus is equal to nu plus mu plus nu minus mu minus. And the answer to the question is there really is no reason. It's just the way we've chosen to define it. It's the way the experts have just decided to do it, and they make the math work from there. They could have chosen not to divide by nu, and maybe further on down the line their calculations would be different. But it's just the convention that people have settled on. Okay, so the next question was asked by Gabrielle. She wants me to explain the density in the Born model and why does the density go from zero inside the ion to suddenly jump up at a certain point. Okay, so let me redraw that plot here. Here I've got the radius out away from the ion center, and then over here I have density. Okay? And then at a certain point, the density goes from 0, 0, 0, 0, 0, 0, 0, and then it will jump up to a point, and the value of that density we would just call the bulk density, or the density of the solvent if there was nothing in it, okay? So she wants to ask, why does it go from 0 and then suddenly jump up there at that point? And here's the reason why. So we have our solute particle right here, and then it's going to have the location of the nucleus, or the center of the solute, and then out beyond it, we may have a solvent molecule, like maybe this is water, and see right there, the two molecules are just barely touching, or maybe they're slightly separated. So that would correspond to a location somewhere out around here. So that's R, that's that distance between those two nuclei. And then if we were to bring them close enough that they were suddenly overlapping, hopefully you're beginning to see the problem there. Like if R is less than a certain value here, then the probability of any molecules doing that is 0. So the density of those solvent molecules too close to the ion is going to be 0. I just realized that Sammy gave a very good answer to this question. So sorry, Sammy, your answer was good too. And that concludes our video. It seems like every other question so far has an answer. So hope that was helpful.